Hi students, so the purpose of today's video is to have a chat about calculating pH. Using the example from class, we looked at hydrochloric acid and sodium hydroxide, 0.1 mole per litre solutions of each, and we did a series of dilutions. So we started with a 0.1 mole per litre solution and we diluted that to 0.01, and that means that we diluted it by a factor of 10. We then continued this process and we went from a 0.01 mole per litre solution to 0.001, and that means we also diluted that by a factor of 10. Now if we went from the first solution there to the third solution, we're actually diluting that by a factor of 100. Okay? Now, I know we didn't all get the results that we were hoping for, or any results at all, to be a matter of fact, but if we had a hydrochloric acid solution of 0.1, that should have been around the 1 mark, theoretically. If we had a 0.01 solution, it would have been around 2. And 0.001 would have been around 3, okay? And then the third one would have been 1 to 3. So if we have a look at what this means, pH is changing with the first and the second example by 1, okay, so it's going up from 1 to 2 and then 2 to 3 by every power of 10 change in acid concentration. So that's the hydronium ion concentration or hydrogen ion concentration. So we can therefore surmise that pH is a logarithmic scale. And if we have a look how we calculate pH, it indeed is. So pH is equal to the negative log base 10 to the hydrogen ion concentration. So we're going to have a look at what that actually means in terms of solutions of acids, just to start with. So what do acids do in water? They ionize in water to varying degrees. That's dependent on the acid that we're talking about, producing a hydrogen ion, a hydronium ion and an anion, again dependent on the acid. So if we have a look at hydrochloric acid, it reacts with water to give us hydronium ion and a chloride ion. And we know now from the Bronsted-Lowry theory of acids and bases that the hydrochloric acid is donating a proton, and here the water is accepting the proton to form the hydronium ion. So here we've got a Bronsted-Lowry acid, and water is acting, in fact, as a Bronsted-Lowry base in this particular reaction. So this is what acids do in water, and this is how we get the production of hydronium ions, okay? And then we simplify this particular equation, which you normally see. HCl gives us the hydrogen ion and the chloride ion, okay? But they mean the same thing. So this is what we're attempting to measure the concentration of when we're measuring pH, okay? So the concentration of hydrogen ions per litre of solution, okay, or the moles. Now we just want to have a chat about what water does, okay? A beaker of water, to a small but measurable degree, will actually react with itself. So two water molecules, okay, of the many, however many there are in the beaker, will bond together, and given enough energy and of course the correct orientation, one will donate a hydrogen ion to the other, forming hydronium and hydroxide. So since this is, you can see, an equilibrium reaction, it is a solution equilibria, we can say, well, there is an ionic product of water, and it's written as follows: Kw equals to the concentration of hydronium ions in solution times the concentration of hydroxide ion in solution. And we know that the square brackets refer to the concentration. Now at standard laboratory conditions, so at 25 degrees Celsius, the concentration of hydrogen or hydronium ions in water is equal to 1 times 10 to the power of negative 7. And the hydroxide ion concentration is 1 times 10 to the power of negative 7. Therefore, using our pH pH equation from the previous slides, pH is equal to negative log 1 times 10 to the power of negative 7. And if we were to calculate that and plug that into our calculator, we would find that that gives us a pH of 7, which we know is the pH of water being neutral. So that's what that means. When we say pH of water is 7, okay, it has got a certain concentration, small concentration of both hydrogen and hydroxide ions, and it's the hydrogen ions that give the pH, that we use to calculate the pH of water, which is 7. Now we can also work out the pOH of water in the same way. So in fact, pOH, which we haven't really referred to much in your junior years in high school, is negative log of the hydroxide ion concentration. So once again, in this particular instance, it's negative log 1 times 10 to the power of negative 7, which also gives us a pOH of 7. So therefore it follows that if we were to add the pH and the pOH, we get a number 14, and that is our pH scale going from, let's say, 0 to 14. So how do we work backwards from pH? Okay, if we work backwards from pH, we actually have the hydrogen ion concentration is equal to 10 to the power of negative pH. Okay, once again, the 10 to the power of is coming from the fact that it's a logarithmic scale. Okay, so some simple calculations, we might just do 1 and 3. If we had a look at 1, we'd look at the pH is equal to negative log of the hydrogen ion concentration, and that's equal to negative log 1 times 10 to the power of negative 6. Okay, and if you remember before, log of 1 times 10 to the power of negative 7 was 7. Well, in fact, we don't even really need a calculator for this. We can say, well, the pH of that particular solution is 6. For number 3, the hydrogen ion concentration is equal to 10 to the power of negative pH. So that would be simply 10 to the negative 2.68. Okay, and you can plug your that into your calculator and you can work out that answer. Calculating the hydroxide ion concentration from pOH, same sort of principle. The concentration of hydroxide ions is equal to 10 to the negative pOH. Okay, so if we were to calculate the solution, the pOH of a solution whose hydroxide ion concentration is 1 times 10 to the negative 11, we would do the same thing. pOH is equal to negative log of the hydroxide ion concentration, and that is equal to, okay, same sort of principle, that's going to be equal to 11. Okay, so that the pOH of that solution is 11. Now, let's say we wanted to work out the pH from that particular solution. We would say, well, pH plus pOH is equal to 14. We know that. So pOH, or pH rather, should be equal to 14 minus 11, which is equal to 3. So the pH of that solution is 3. It's actually an acidic solution, okay, but we've worked that out using pOH instead of pH. So you will be asked to calculate a variety of pOHs and pHs, and hydroxide ion concentration and hydronium ion concentration in class next lesson. So I hope that that prepares you, and you can by all means do the examples that are given here as well in your books. Okay, I'll see you next lesson. Thanks everyone.